Now that we've discussed the concept of magnetization, we can try to put it into our systems of equations that we've developed up to now to see what kind of field can be produced by a chunk of matter having a certain given magnetization M. So where do we start from? Well, we had discussed the vector potential, and in particular, we had written down the vector potential created by a single isolated magnetic dipole with moment m. And this was given by this expression here, just m crossed into the distance vector, and in total a 1 over r squared dependence. Now, if we have a big chunk of matter with a given magnetization big M here, by the principle of superposition, so by linearity of all fields in electrodynamics, we can just obtain the total vector potential by integrating over all regions where the magnetization is non-zero, and just use the formula for the dipole contribution to give us this volume integral here. So the vector potential is just the volume integral of m crossed into the distance vector with a 1 over r squared. Okay. So this expression is completely legitimate. It's really good enough for most purposes. However, similarly to what we did in the electrostatic case, it's possible to have a convenient rewriting of this, leading to an equivalent expression in terms of what we will come to know as the bound currents. So how does it work? Once again, we put our mathematical hats on for a few minutes. The derivation of this itself is not interesting. It's the result that's interesting. So I'll just run you through the derivation very, very briefly, so you've seen it once in your life and can refer to it if ever you need to later on. How does it go? It looks very, very similar to what we did. We start by just rewriting this this r over r cubed vector here as the gradient with respect to the source coordinates of the scalar 1 over distance. Okay, so I've just used this identity here to rewrite this. Now, what we do is a partial integration. So here we have a vector, curl another vector, but there's a derivative here. And what we can do is kind of take this derivative out of the product here. So if we look at the curl of a product, so here the kind of basic identity is here. You'll find it in the lecture notes. Here I'm taking the curl of the product of a scalar field with a vector field. Okay, and in that case, curl of this product here is just grad of the scalar field crossed into the vector field plus the scalar field with the curl of the vector field. So I'm going to use this identity here to rewrite this term, just identifying A with the M and psi with 1 over R. I'm going to rewrite this as the curl of this product with the correction coming from then the curl of A, which is really the curl of M. Okay, so it's just like partial integration logic here. I rewrite my volume integral of this thing by just reapplying the differential operator the other way around. Now, so what does that give us? Well, we have to make use of a little identity that actually comes more or less freely from the divergence theorem. So once again, I emphasize this is for your information. This is not really stuff that I want you to know by heart. This is just an identity that that comes in the derivation of this interesting equation that we're about to get to. So what does this say? It just tells you that the volume integral of the curl of a certain vector field corresponds to the surface integral of the vector field with the cross on the differential surface element on the surface. So here, of course, as usual, the volume is circumscribed by a certain surface. So here I'm doing the integral over the surface bounding this volume V. Okay, so you can look at the proof in the blue box here if you're interested. It's just really literally using the divergence theorem for an object, which is the cross product between a spatially dependent vector field and just a constant vector, and then realizing that the identity is true for any vector here, and therefore that this identity is true. Okay, once again, this is just for information purposes, so you have it. The point is that when we have this identity at our disposal, we can just use it straight to rewrite the second term that we have in here in terms of a surface integral. So as an identity, we've rewritten our vector potential as the sum of two terms, one volume contribution and one surface contribution. So in the spirit of the Biot-Savart law, if you want, this is like having an equivalent system that contains bulk currents and surface currents generating the same vector potential as the original magnetized piece of matter. Okay, exactly the same interpretation as we did in the electrostatic case. So you can now interpret this curl of the magnetization here as a bound current inside your piece of matter. And also the M crossed into the normal of the surface here as a bound surface current. So what does this tell you? It tells you that if you have a chunk of matter in which you've got lots and lots and lots and lots and lots of magnetic moments here and there with spatially dependent amplitudes, then as far as the magnetic field or the vector potential is concerned, this is the same thing as the same shape piece of matter, but containing a certain current inside it and a certain surface current on its surface, where these are the bound volume and surface current. Okay, so the magnetic field issuing from these two situations is absolutely mathematically the same. So for example, if you had a chunk of matter that was uniformly magnetized, the magnetization would be a constant, and therefore the curl of this constant would be zero, because that contains a spatial derivative. So if you have a uniformly magnetized chunk of matter, you can replace it by just a surface with current on it, current given by the cross of the magnetization with the normal vector that you have here. But in the bulk, there would be nothing. Okay, it would be completely equivalent to that. So this is just a handy rewriting that very often becomes useful when you've got situations where you do happen to know something about the value of the magnetization and you want to simplify your calculations of the magnetic field coming out of it. But I emphasize this expression here in terms of bound volume and surface currents is absolutely mathematically identical to the original equation that we had of the vector potential given as the volume integral of the magnetization crossed into the 1/r². Okay, so this is just exactly parallel to what we did in the electrostatic case. It's just using different objects, different notations for a certain thing. Instead of doing a scalar potential, we're now computing the vector potential for the magnetic field.